Hi everyone, this is the first of two videos to watch for Thursday, March 19th. So this video is going to be based on understanding pedigrees. First we'll go over several basic Mendelian patterns to refresh your memory from intro genetics, and then I'll show you a few pedigrees where there are more complex patterns. After you complete watching this short video, please go ahead and also watch video number 2 about genetic mapping. And that's a topic you'll be writing about for your research paper. Looking ahead at the bottom of the slide, you can see for next Tuesday, March 24th, assignment 11 will be due, uploaded in Blackboard by 11 a.m., again on Tuesday, March 24th. This assignment is posted already, and it's based on the Watkins et al. Paper. This is a fairly short paper. It will be graded on the amount of effort, but please use discussion boards to try to work together as needed. Answers will be posted after the deadline. For next week, you should be watching the additional videos that will be posted for March 24th, and as soon as possible, begin work on draft 1 of parts 1 to 3 of your research paper. Again, you want to start right away because you need to allow time for interlibrary loan to get the materials that you may need that are not available for free. I've posted instructions for how to use interlibrary loan in the research paper tab. If you have any questions, please email me. I've also noted in green at the bottom that to find articles, OMIM is very helpful, as I mentioned in the March 17th video, but PubMed is another very helpful tool, especially if you want to find review articles. So for example, you can type the name of your disease, like my disease choice was cystic fibrosis, and then you type and review. And this will pull up review articles that give a lot of the basic information you'll be looking for parts 1 to 3. Okay, so the overall pedigree analysis tips are to first, when you're looking at a pedigree and trying to determine the mode of inheritance, check to see if the trait appears in both males and females. You want to be careful not to overinterpret unequal numbers because pedigrees are generally fairly small. So, right, those numbers of offspring in any family are quite limited. If it's close to equal, however, it's most likely autosomal. If there are more males, it could be X-linked recessive. And if there are more females, it could be X-linked dominant. You won't see many pedigrees that are Y-linked traits, but if you saw only males, it could be Y-linked. Second, you want to check to see if the trait skips generations. If yes, it's most likely recessive. If no, it might be dominant, but it could be any mode. The third step is to check to see if affected individuals always have an affected parent. This will always be true for dominant traits. So if it is not true, you can exclude autosomal dominant, and usually X-linked dominant. The fourth step is to ask if all of the daughters of affected fathers are carriers, and whether or not more males are affected. Those are two signs of X-linked recessive pedigrees. And the fifth question could be to ask if all daughters and no sons of affected fathers are affected. And that is the characteristic specifically of X-linked dominant traits. If you want to be very sure of whether or not you have the correct mode of inheritance, what you would want to do is assign genotypes to make sure there's no inconsistencies. But as we will talk about, not all traits follow basic Mendelian inheritance rules, so sometimes you will see inconsistencies. Okay. We might see. So here's a second pattern. It looks quite different. First of all, you can see that there are squares and circles. So we see both males and females that have dots in the middle. Those are carriers. Sometimes they're halfway filled in, and sometimes they have dots to indicate carriers. We also see in the third generation a double line, and that indicates a consanguineous marriage, and that is when two people who are closely related have a family together. Okay. So what do we see in this pedigree? We see it is not appearing in every generation. We have one male and one female affected, so there does not appear to be a bias there. And clearly, the affected individuals do not all have affected parents. Okay. And I mentioned briefly that we see this instance of consanguinity that we don't typically see in most pedigrees. So with all of these characteristics in mind, this is most likely autosomal recessive. Skipping generations, we see both males and females affected, And because the carriers are indicated, we can see that for each affected individual, both parents are carriers. So when you looked at this in intro genetics, it might have been, for example, in generation 3, individual 1 would be big A, little a, individual 2 would also be big A, little a, and so those individuals would have a 25% chance of having a child who's little a, little a. So that would be child 3 in generation 4. Okay, what is a third type of pedigree we might see? So this pedigree also skips generations. We only see 2 affected individuals, and that's in generations 3 and 4. And they're both males in this case. So what does this tell us? Because it's affecting mainly males, and we see again the affected individuals don't have an affected parent, there's no male-to-male transmission. Again, with only 2 affected individuals, it's not a lot to go on, but instead of seeing a male-to-male transmission, what we see is that both of the males affected have mothers who are carriers. And this is characteristic of an X-linked recessive trait. So overall, X-linked recessive traits, remember, are going to skip generations, and we're going to see more males than females affected, and the males will have affected mothers, carriers, mothers who are carriers, right? That's where they're going to get that X little a from their mother. Okay, so that's X-linked recessive. And lastly, a fourth type of basic Mendelian inheritance pattern we might see is shown here. We see a lot of affected individuals, and the characteristics are that we see the trait in every generation. More females than males are affected, so this is opposite of the prior pedigree. Every affected individual does have an affected parent, so that's typical of dominant traits. And this is a very important pattern to look for. All the daughters and none of the sons of an affected male are affected. So in generation 3, individual 3 is an affected male, and he has a large family, so we can easily see that he has 1, 2, 3, 4 affected daughters, and none of his sons are affected. That is characteristic of an X-linked dominant trait. Okay, so those are your 4 basic Mendelian inheritance patterns that you might see in pedigrees, but the reality is that with genetics, it's often more complex. As we talked about last time, that most of the most common genetic diseases are actually complex and not just monogenic. And therefore, these pedigrees are not going to follow those rules that we just went over. So here is one example of a situation where you can see that for the most part, at least 2 of the 4 affected individuals have an affected parent. We can't see the parents of generation 1. We see both males and females are affected. So this looks like it could be a dominant trait. However, we see that arrow is pointing to individual 2-2, right, that circle. This is a female who phenotypically is unaffected, and this is a situation of incomplete penetrance. So that female, although she does not show the phenotype, actually has the allele to pass on to her daughter, in this case, to continue transmitting this trait or genetic disease. So the arrow is something used to indicate what's called a proband, or an individual in a pedigree of particular interest. So if a genetic counselor or a researcher trying to determine the inheritance of this trait was looking at this pedigree, and they had other pedigrees as well that were consistent with autosomal dominant, they might draw that arrow there to say, okay, here's one inconsistency, but that could be explained by incomplete penetrance. Okay, that's one example. A second one is shown here. This one is unusual, where you see different quadrants can be filled in. For example, in generation 2, the third individual has like 3/4 of the circle filled in. Person number 6 in generation 2 has only the top left quadrant filled in. So what's going on with this pedigree? This is autosomal dominant with variable expressivity. So you see that every individual who does have any part of their symbol filled in does have an affected parent. This is actually Waardenburg syndrome, and shading of the first quadrant, kind of going clockwise from 12 o'clock, is hearing loss. If quadrant 2 is filled in, that means the individual has different colored eyes. If quadrant 3 is filled in, they have a white forelock. And if quadrant 4 is filled in, they have premature graying of the hair. And as you can see, of course, some individuals have more than one quadrant filled in. So they would have more than one of these traits. So this is an interesting and not, I don't remember the incidence exactly, but not super uncommon. I know a family that has Waardenburg syndrome. And in general, everyone does pretty well. This is not one of the more serious genetic traits that we see. And the last example I'm going to show you today of pedigrees is shown here. This is different from any of the other pedigrees we've looked at because we have these two very small squares. In generations 2 and 3, there are very small squares that are filled in. So what is going on in this situation? Well, this is a pedigree of incontinentia pigmenti. This is an autosomal dominant trait. However, the affected males abort spontaneously. So those are those small squares. So you never see an affected male. So when you first look at this pedigree, you would see only affected females, and that might actually sway you in the wrong direction. So only if you actually knew that that the affected males had ever been conceived would you have a better understanding that both males and females could be affected, at least for a short period of time. Okay, so that's our last example of a complex pedigree, and at this point you should go on to watch the second video for March 19th. Thanks.